So now we understand why this rotational axis is stable. But what about the other two? Why is this one stable and why is this one unstable? Well, these two other axes of rotation actually behave the way they do for the same reason. It has to do with the fact that whenever an object rotates, its axis of rotation always has to go through its center of mass. This is because if the object is rotating around another point way up here, its center of mass, which is the average location of all the mass in the object, would be traveling in a curved path. And as you know, all objects tend to move in a straight line if there isn't a force acting on them. So in order for a rotating object to, on average, be moving in a straight line, it must rotate around its center of mass. But what would happen if I tried to force an object to rotate around an axis that did not go through the center of mass and then let it go? For example, what would happen if I tried to spin the stick like this and then let it go? Well, the forward momentum of the bottom part of the stick, which is much more massive than the top part, would overwhelm the backwards momentum of the top part of the stick. So it would start moving forward. But what would happen to the axis of rotation? Well, if you've been paying attention to this video at all, you would say that it would naturally tend toward the center of mass. And you would be right. As soon as I let this object go, it would start spinning around its center of mass and moving forward at the same time. But wait a second. What is an axis of rotation? According to the Merriam-Webster Dictionary, an axis of rotation is the straight line through all fixed points of a rotating body around which all other points of the body move in circles. But what do they mean by fixed points? What are these points fixed relative to? Well, you'd think they'd be fixed relative to a stationary observer. But if you use this definition, then the axis of rotation of an object that is spinning and moving overall in a straight line at the same time, the axis of rotation actually fluctuates. If you look at this stick that is spinning and moving forward at the same time, when it's in a vertical position, the backwards motion of the top part of the stick when it's spinning counteracts the overall forward motion, so part of the top of the stick isn't moving. There's a line of points somewhere up here that is still, and you could consider this as the axis of rotation. Later, when it goes to horizontal, all the points on this side of the stick are moving down and all these ones are moving up. So obviously, the axis of rotation goes through the middle where the center of mass is, because those points are moving in a straight line and all the other ones are moving in circular curves. But when it's back up here in another vertical position, flipped over, again, a part of the stick up here appears to be fixed. So, the axis of rotation started up here and then moved down to the center and then moved up to the other side. And if this object keeps spinning like this and moving forward, the axis of rotation will keep flipping back and forth. But this actually isn't the right way to think about the axis of rotation in this particular situation. because if you could catch up to this moving object and move at the same rate as its center of mass, you would see that the axis of rotation does actually go through the middle where the center of mass is and doesn't fluctuate up and down. But this sort of thinking actually does apply in another situation. Now, let's figure out why this rotational axis of the rectangular object is stable and this one is unstable by using this pencil to represent the rotational axis. We will also put a small deviation in the spin because no flip is going to be perfect. And then we will use the logic we just learned to figure out how this rotating system will evolve. For starters, let's look at the rotational axis that goes through the longest dimension of the object. And let's put a very large deviation in the spin so the effects we will be looking at are easy to see. But before we start, let's make a rule that when the pencil is pointing this way away from us and we're looking at the bottom end, then the object will be rotating clockwise from our perspective. And if it's pointing toward us, then it will be rotating counterclockwise from our perspective. Now, if you look at this entire object at once, you will see that the axis of spin goes through the center of mass. But if we just look at one half of the object individually, you will see just by eyeballing it that the mass is very unevenly distributed on each side. There's a lot more mass on this side than this side. So just like with the wooden stick I showed you earlier, if the object is spinning around like that, then the upward momentum of this side of the object will overwhelm the downward momentum of this side, so it will gain an overall momentum upward. Now, if we look at the other half of the object, the opposite thing will happen. Because it's spinning like this, the downward momentum of this larger side of this half will overwhelm the upward momentum of this side, and so this half of the object will gain an overall momentum downward. So this side will gain momentum upward, and this side will gain momentum downward. This creates a torque going this way. But what will happen to the axis of rotation? Well, just like with the wooden sticks, it will shift so that it goes through the center of mass of each of the halves of the rectangular object, as well as the main one at the center. But we also have to consider the rotational force created by the unevenly distributed mass of the original spin. This torque can be represented by a spin axis that looks like this. This spin can actually be divided into a part going this way and another part going this way. If you were to spin up this object with a certain amount of angular momentum along this axis and another amount along this axis, you would get it spinning exactly like this. So if the object is spinning with its axis like this, with a certain torque this way, then the part of that torque that's spinning this way will cancel out the part that's spinning this way. So you'll be left with some angular momentum this way and some angular momentum this way. If you look at how this will play out, by rotating it like this and like this at the same time, then you can figure out where the overall axis is by looking at which part of this is still relative to the center of mass. Remember that the axis of rotation is a line of points that appear to be still and that everything else in the object rotates around. So if I try and figure out where the axis of rotation is by spinning it like this, I find that at this part of the object, its momentum this way cancels out its momentum this way. So this part appears to be still. A similar thing also happens at this bottom left corner. Its momentum this way cancels out its momentum this way. So it too appears to be still. So now these 2 points are still relative to us and relative to the center of mass. So the rotational axis is here. Now, if I continue to evolve this into the future, I will see that when this side comes around, the momentum, instead of canceling at this point and this point, will cancel at this point and this point, because the momentum this way will cancel the momentum this way, making these 2 points the new still points. So now the axis is here. So the axis started off like this and then flipped to here. And then, because the same effect that we just discussed will happen again, it will flip back and continue flipping back and forth. This is just like the stick we saw spinning and moving forward at the same time. From our perspective, the axis of rotation flipped up and down the stick. But when I was demonstrating with the wooden stick, I said that this isn't the right way to think about the rotational axis. But in this case, it is, because our perspective is the same as the perspective of the center of mass, because we are assuming, for simplicity, that the object has no overall straight line motion relative to us. So, what we consider to be still, the center of mass also considers to be still. Remember, the axis of rotation is just a line of points that are still relative to the center of mass, and that everything else in the object rotates around. So, if this line of points is still relative to us, then it is also still relative to the center of mass, and so is the axis of rotation. The reason why this flip-flop reasoning was wrong with the stick that was moving forward and rotating at the same time is that the center of mass was moving relative to us, so what we consider still isn't necessarily still relative to the center of mass. So our perception of what the axis of rotation is incorrect. Now, even though the axis of rotation is changing, its deviation from a perfect flip never becomes greater than the deviation in the original spin. So if the deviation is very small, like this, it will stay small and never grow exponentially large like it does with this axis that we'll get to later. This is why this rotational axis is stable. It self-corrects. Now we understand why this rotational axis is stable and why this one is also stable. But why is this third one unstable? To find out, be sure to subscribe to my channel so you are notified when part 3 of this series comes out. There I will explain the final part of my theory, which explains why the rotational axis that goes through the intermediate dimension of this object is unstable. Thanks for watching.